Good day, this is Jim Pytel from Columbia Gorge Community College. This is Digital Electronics 1. This lecture is entitled Unit 3 Review. Okay, so we went over a bunch of things this particular section here, and what we're going to do is we're going to start off with a review of all our gates, kind of the rogues gallery of gates here. What I want you to do, for every single one of these gates I've drawn on the left-hand side, I want you to come up with a name, kind of the verbal logic description, a truth table for it, give me the written expression on the VHDL expression. From then, what we'll do is we'll actually do timing diagrams for every single one of these gates. So let's start off with the first one. First one, it's a NOT, and I'm referring to this one right here. It's a NOT gate, often called an inverter. What's its logic description? Just say it inverts it, or changes it to its opposite value. If the input A, I'm drawing a truth table here, our output X. A is a 0, output's a 1. If input's a 1, output's a 0. What's the written expression for it? X is equal to not A. Not A, not A. There's a number of ways of writing that thing. You can also see this in Verilog, which is a different type of language. What is the VHDL expression? X is assigned not A. Typically, they're expressed as lower. It's case insensitive. Constants are typically expressed as uppercase. Go ahead and try the next one, this guy. Okay, that's an AND. Its logic description, to me, output is high if all inputs are high. Come up with a truth table given inputs A and B. What's our output? X. Output is high if all inputs are high. What are the others? What is the written expression for AND? X is equal to A ANDed with B. Sometimes you don't need that. Sometimes if people write it out with a keyboard, they use the asterisk, however you pronounce that thing. The VHDL expression, X is assigned A and B. Okay, next one. Looks just like the one we just did, but its output is inverted. So that's what's known as a not AND or a NAND. The logic description for that one, output is low if all inputs high. What's the truth table look like? Output is low if all inputs are high. The rest of them get ones. What's the written expression? X is equal to A ANDed with B, then the whole thing is inverted. How do I write this in VHDL? X is assigned A and B, all in parentheses, knotted. So not parentheses A and B, close parentheses. I can just as easily A NAND B. Write it that way. Okay, next one. Okay, so that looks like an OR gate with the inputs inverted. So that's what's known as a negative OR. Okay, the logic description that I'm going to use for a negative OR, it's kind of describing the exact same truth table we had for the gate above, but it's coming from a different perspective. And that's the output is high if any input is low. That's kind of the negative logic perspective. What's the truth table for that? A, B, X. By the way, they all have A and B for our inputs, with the exception of the inverter, which just has A. And I'm saying all of them have X as the output, not tied together, which is a good point. I need to actually talk about tying outputs together. I don't ever tie outputs together. 0, 0, 0, 1, 1, 0, 1, 1. Output is high if any input is low. High, high, high. The rest of it gets 0. It's the exact same behavior as our NAND. It's just a different way of looking at it. What's the written expression, however? So if it's ORing together, so the negation of the inputs, okay, so that's the written expression for a negative AND. And if you remember right, that should be logically equivalent to A ANDed with B and the whole thing negated. So that's from the NAND perspective, negative OR perspective. Okay, if I wanted to write the VHDL expression for a negative OR, what would I do? I would say not A or not B, closing those semicolon, which is just as functionally equivalent as saying is A NAND B. So those things are functionally equivalent, the negative the negative OR and the NAND. All right, let's do our next one. That is our XOR gate. Now, a million points off if you said XOR. It's called an exclusive OR, even though it's spelled XOR. What is the logic description? I like to describe it as output is high if the inputs are different. And a more accurate description, this is the one I like using, the more accurate description, because this describes a multi-level one, if the inputs are odd. When I say odd, is an odd number of them, not if they're weird. Okay, the truth table. A, B, X. Let's go back to the different. 0, 0, they're the same. 0, 1, they're different. 1, 0, different. 1, 1, the same. What is the written expression for the exclusive OR? X is equal to A exclusive OR B. What is the sum of products expression for the exclusive OR? When is it high? When A is a 0 and B is a 1. Or when A is a 1 and B is a 0. Okay, that is the SOP implementation of that. And I should be a little bit more clear in that by using that expression. Okay, that's the sum of products expression. You can write the exclusive OR as that. And trust me, that works. What does this thing look like? It's two AND gates feeding an OR gate. Got A on this input, B on that input. This one's inverted, this one's not, that one's not, this one is. Not A, ANDed with B, A, ANDed with not B. What do you get as the final result? That guy right there. Not A and B, or A and not B, which, if you want to be fancy, A exclusive OR B. Okay, how do you write this thing in VHDL? Well, like I said, it's such a common gate, it's got its own special word. X is assigned A exclusive OR B, semicolon. If I wanted to write the SOP expression, how would I do that? In VHDL, X is assigned not A and B, or not, actually I'm going to write this on one line. Okay, there you go. X is assigned not A and B, or A and not B. Do I need parentheses? Not really. Will it make it more readable? Yes. If I want to be absolutely certain, I can do something like that too. A little bonus about VHDL order of operations there. Okay, so what is our next gate? Oh my gosh, it's one of our basic gates, the OR gate. What's the logic description? Output is high if any input high. What's the truth table? What's the written expression? X is equal to A or B. The VHDL expression, X is assigned A or B, semicolon. What's the one immediately below it? Well, it's kind of the inverse of that. It's a NOR. The output is low anytime any input is high. It's the inversion of the one we just went over. What is the written expression? A or B, the whole thing negated. How do I write that in VHDL? X is assigned A or B in parentheses, not. So not parentheses, A or B, parentheses. Like I said, they're so popular, they get their own name, A nor B. What is the logic gate immediately below that? Looks like a AND gate with its inputs inverted. So I'm going to call that a negative AND. So it's kind of looking for zeros on those inputs. What I'm going to say is output high if all inputs are low. What's a truth table like that look like? A, B, X, 0, 0, 0, 1, 1, 0, 1, 1. Output is high if all inputs are low. Oh my gosh, it's the same truth table. And by the way, we were talking about this guy as the one we just discussed. So it's the negative logic equivalent of the NOR. So negative AND, I could say, is equivalent to a NOR. The written expression for a negative AND is I am negating A, negating B, and ANDing them together. It means it's functionally equivalent to A or B, the whole thing negated. So the written expression, which I just wrote for a negative AND, is A negated, B negated, ANDed together. What is the VHDL expression for that? X is assigned not A, not B, ANDed together, semicolon. If you want to be very concise, go ahead and put those things in parentheses. And if the negative OR and the NOR are functional equivalent, I can just say this too, A nor B. Last gate looks like an exclusive OR with a bubble on it, so it's inverting it. So that's what's called an exclusive NOR. It's not an XNOR. The logic description, if the description for the exclusive OR was it's high if it's different, then I'm going to say it's high if it's the same. More accurate description might be high if all the outputs are, if they're an even number of ones in the inputs. That's for two input, but I like kind of calling it high if it's the same. What's the truth table? Same, different, different, same. It's the opposite of the exclusive OR. What's the written expression? X is equal to A circle dot, which means exclusive NOR B. What is the SOP expression for this? There's the ones. What I'm going to do for that first one, invert A, invert B, feed them into an AND gate. Here's the second one, A and B, feed them into an OR gate. So that's an SOP, sum of products, implementation of an exclusive NOR. What might that say? That is not A, ANDed with B. That's that one's output. What's this one's output? A, ANDed with B. What are they being done? They're being ORed together. So what I get is not A, and not B, or A, and B. It's my output for X. How would I write this? The original expression, exclusive NOR in VHDL, like I said, it's very popular. X is assigned A. It's got its own special name, exclusive NOR B. How would I write the SOP expression in VHDL? X is assigned not A. And go ahead and do this all and kind of illustrate what I'm talking about. So not A and not B, or A and B. Do I need parentheses? Not really. Do I need a semicolon? Yes. In parentheses, what I could do is do this, and do this, and do this, and do this to make sure. So now we've gone over every single one of these gates. Let's go ahead and put these in a timing diagram and see if you can come up with some answers here. Okay, so here we go for the first empty timing diagram here. We've got A being fed into an inverter. Go ahead and give me the output for that one. So go ahead and pause the recording and see if you can come up with that. I'm going to do my best estimate here. That to me is the inversion of A. The second blank timing diagram, what you're going to do is take A and B. Go ahead and see if you can come up with your estimate of what that would look like, A and B. That's what I get right there. Anytime all inputs are 1, the output is 1. Okay, the third blank timing diagram, it looks like A or B. Let's go ahead and see if you can get your estimate of it. Okay, there you go. Anytime any input is high, the output is high. Okay, let's do a little bonus round here. What would A ANDed with a 1 look like? I would say it looks startlingly similar to A. Here's a couple of really good practice exercises for you. What about A and 0? What about A or 1? What about A or 0? Okay, so those are good practice exercises right there. Okay, so let's go ahead and clean this up and add a couple more gates onto this. Here we go. In that first one, looks like we got A NANDed with B. Okay, go ahead and see what you think this timing diagram looks like. Go ahead and pause it, and I'll go ahead and fill it in. There you go. The output is low when all inputs are high. Go ahead and see if you can come up with the second timing diagram there. It looks like a NOR gate, NORing A and B. There you go. The output is low if any input is high. Go ahead and see if you can do the third one. What that is an exclusive OR of A and B. There you go. It's different there. It's different. It's different. It's different. Different, different, different. What does the exclusive NOR look like? It's just the inversion of that. Or you can just say it's the same because they're both 1. It's the same because they're both 0. It's the same because they're both 1. And finally, it's the same because they're both 0. So that kind of concludes our 2 input gates. Let's go ahead and move on to some multi-level logic circuits, and we might even start incorporating expanded inputs to these basic gates. Okay, so let's go ahead and try a multi-level logic circuit using some of these intermediate logic gates here. And what we want to do is we want to come up with 3 tasks here, get a truth table for the ultimate expression, find the written expression, and let's go ahead and write the VHDL expression for it. And we've got our truth table with all possible combinations of inputs A, B, and C. And we want to go ahead and come up with the truth table for X. And what I'm going to say is give yourself some room. Use those intermediate signals. I'm going to go ahead and grab a signal there. I'm going to call it L. Now it's M. That's N. So what is L? Looks like L is A or B. You can put that expression right over it if you want to. Kind of reminding yourself what that is. What's M? M is not B. And finally, N. What is N? It's A ANDed with C. What's our expression X? Well, it's the NAND, the not AND of L, M, and N. So what we're going to do is we're going to take L, M, and N, AND them together, and then invert the result. Or the only time it's low when all inputs are high. So just fill out the column for L when A or B. There you go. Okay, what's not B? What's N? It's A and C. Okay, basically I'm picking out those times right there when both A and C are high, because that's the only time an AND gate would be high. And I'm going to go ahead and fill out the rest. And now what I'm looking for in the terms of X is when all inputs are high, my output is low. There you go. Okay, that's the one and only time my output goes low. All the rest, and because I want to be a jerk, what if I did something like this? Took the negative logic equivalent of a NAND gate, i.e. a negative OR. Would that affect our output at all? The answer is no. Okay, what is the negative logic equivalent? It's the output is high anytime any input is low. We're looking at this section of the truth table here. The output is high anytime any input is low. It's the same thing, just looking at it from a negative logic perspective. Okay, let's go back to our NAND, our original. Let's go ahead and now come up with our written expression. We've got the truth table. Let's go ahead and come up with the written expression for it. Just use your intermediate values. What's x? Well, it's x is equal to L, M, and N anded together, negated. What's L? L is A or B. What's M? It's not B. What's N? It's A and C. The whole thing negated. It looks ugly. There are ways of simplifying this thing, which we haven't discussed thus far. We will in a next lecture, but that should be the written expression for it. Okay, we'll make it pretty next unit. Okay, how do I write this in VHDL? What is the expression, the written expression for x? X is assigned not L and M and N. What's L? So we got to use that same multi-level logic circuit analysis technique using those intermediate values. What would L be? So L is assigned A or B. M is assigned not B. N is assigned A and C. This is again if you're using those internal. This is begin and end. We've got those internal signal declarations up there. Let's pretend we don't want to use internal signal declarations, L, M, and N. What I want you to do is I want you to write this whole expression all in one line. Let's go ahead and clean it up so you can see what that looks like. And there you go. That's the big old expression right there with some major problems regarding syntax because I haven't put any parentheses in there. What I'm saying is not L anded with M anded with N. I'm going to clean up this thing at the end so you can see what's going on here. Okay, so our final VHDL expression should be x is assigned not parentheses, A or B parentheses, and parentheses not B parentheses, and parentheses A and C parentheses, semicolon. So let's move on to another example using SPLD and try to come up with the SOP expression. Here is our PLD device, which we have just bought off the shelf. Notice that there are no inputs connected to any of those ANDs, but all those ANDs are in fact feeding a single OR gate. So what we're going to do is we're going to take this device and program it to do whatever function we want. And what we're going to do is we're going to go ahead and write a VHDL program. We send it to our device and it connects it in the following fashion. There you go. I know it might be confusing. You've got 8 inputs to 4 AND gates, which are all feeding an OR gate. Remember I said that about the SOP. It's and one-line notation. Just look at it from the perspective of a single AND gate, namely this one. What is that AND gate's inputs? Okay, so for that first one, looks like it's connected to not A, ANDed with not B, ANDed with C, ANDed with D. And then just forget about it. Move on to the next one. What's this guy's inputs? Not A, ANDed with B, ANDed with not C, ANDed with D. Again, forget about it. Move on to the next one. I'll go ahead and let you do the next 2. And if you've done it correctly, you should be getting that one and that one. Now, ultimately, what is happening to all these AND gates? They're being ORed together. So what I can do is I can just say OR. If I want to write it out long ways, it's going to look like this. So what I've got is that my first term, not A and not B and C and D, ORed with not A and B not C and D, or together with not A and B and C and D, or together with A and not B and not C and D. That's what's my final expression, X. Let's go ahead and see if you can fill out the truth table for this. Okay, this might be complicated, but what I'm kind of give you guys a hint here. Pull this up. Actually, let me make this clean. Look at each individual AND gate. Specifically, start with the one on the left. There's only 4 inputs, A, B, C, and D. And I know you've got the complements or their inversions available. If you feed in all 4 inputs, some version of all 4 inputs in there, into an AND gate, what you're going to get is the one and only combination, which will make that AND gate 1. What is the one and only combinations of A, B, C, and D that will make that AND gate output a 1? Think about it. D could be a 1. C could be a 1. B could be a 0 because it's being inverted. A could be a 0 that could be inverted. So what I'm going to say is that's 0, 0, 1, 1 for A, B, C, and D. When A, B, C, and D are respectively 0, 0, 1, 1 being fed into this whole array, this output, the output of this AND whose expression is not A, not B, C, D, will output a 1. And because it's an OR gate, the whole expression will will output a 1. Does that make sense? So 0, 1, 1 is going to have a 1 output. So this is kind of a shortcut. We've already taken care of the one circumstance that that AND gate will produce a 1 output. And go ahead and test that. Just test out that single AND gate for any other combination in that 16 different combinations. The one and only time that one AND gate produces a 1 is that unique combination 0, 0, 1, 1. I'm going to do this example right here. The second term, the second AND gate, not A, ANDed with B, ANDed with not C, ANDed with D. What is the one combination of inputs that will make that one a 1? Well, if A, B, C, and D are respectively 0, 1, 0, 1, when I take the expression not A, B, not C, D, what I get is a 1, 1, 1, 1 being fed into that second AND gate, which outputs a 1. And because that OR gate is there, if this one's outputting a 1, the output for that OR gate is a 1. And try it for all their possible combinations of input. That's the only time that the second AND gate produces a 1. So where was that? It's right here. Go ahead and see if you can do this analysis, this type of analysis. And this may be a little hard for you for this guy and this guy. I'll go ahead and pause the recording and see if you can come up with a one and only time combinations that those will give you a 1 for those AND gates. Okay, so for third AND gate, a combination of 0, 1, 1, 1 on A, B, C, and D will make the AND gate in this beautiful shade of pink output a 1. And because it's feeding the OR gate, that's going to be an output of 1 right there, right there. And that's the one and only combination that particular AND gate is going to output a 1. Don't believe me? Test it out. Finally, this one, when does he output a 1? Respectively, when A is a 1, B is a 0, C is a 0, and D is a 1, because it's A, not B, not C, ANDed with D. All those ANDed together, what are you going to get out? Is an output 1 right there. On that particular AND gate, all the other AND gates will be producing zeros. What is the output? It's a 1. Where is this on the truth table? Right there. Trust me, run through all possible combinations of input right there. All the other possible combinations are 0. So what we've kind of designed is our first combinational logic circuit. This is a greater function. This is a circuit that's designed to detect the number 3, 5, 7, and 9. Pretty cool, huh? What we're using is this programmable logic device, which we can reprogram the next day to detect other combinations of numbers. And this is kind of a brief introduction to the sum of products expressions, which we'll be going over next week here. But ultimately, what we are is we're looking at a multi-level logic circuit. What does the one in the yellow, the one in the pink, the one in the green, one without highlighting, we're using those intermediary expressions, and we're ORing them all together. What would this look like in VHDL? A nightmare. We'll go into that one later. But for the sake of completeness, I'm going to go ahead and write it out for you. The first one, the unhighlighted one, is parentheses not A and not B and C and D, close parentheses, or the second one, the yellow one, parentheses not A and B and not C and D, parentheses, or the third one, parentheses not A and B and C and D, or the fourth and final one, parentheses A and not B and not C and D, close parentheses, semicolon. There's easier ways of doing that, but it's a good exercise in VHDL coding. One thing here too is check this out. So you got your 3, 5, 7, and 9, and you go ahead and put your LED, it's your 3, 5, 7, 9 detector right there, and anytime you see a 3, 5, or 7, or a 9, the LED lights up in a sourcing arrangement. What about this? It's a syncing arrangement. What lights up now? Well, 0, 1, and 2, 4, 6, 8, 10 through 15. The zeros make it light up. But let's say you still want 3, 5, 7, and 9 to light up in a syncing arrangement. What am I going to do with the output? Put an inverter there. What's the inversion look like? It's giving a 0 at 3. It's giving a 0 at 5, giving a 0 at 7, giving a 0 at 9. It lights up. But let's say I want it to be more useful than this. Let's say I want the output of this thing to light up in a syncing arrangement or a sourcing arrangement. Basically, I want to have a customizable circuit that I can feed either a sourcing arrangement or syncing arrangement. How about this? Here's an application. Put an exclusive OR. That is an exclusive OR. It's really ugly looking. At the output, where does this one go if I want it inverted? Where's that one go if I want it not inverted? So if I want to keep this thing in the non-inverted, i.e. the sourcing, what I'm going to do is put a 0 to that. It's a selector switch. Selective inversion. Trust me, it works. Go back and review the exclusive OR lecture, or just do it yourself here. Exclusive OR the output with a 0. Now, if I want to invert it, exclusive OR the output with a 1. It's inverting it once there's a 1 on the second output of the exclusive OR. So that's a pretty cool application. Either source or sync that thing. One last note about multi-level logic circuits. Let me draw something for you here. What is the output X of this circuit? And if your answer is anything other than a headache, you're wrong. I've seen this picture. I've seen this picture in some reputable, otherwise reputable textbooks. Never, ever, ever tie outputs together. You can tie inputs together all day. You can tie inputs daisy chaining to other gates. A can be fed to 3 different gates inputs. Never tie outputs together. And here's the reason why. What if A and B produces a logical 1? 5 volts. What if C and D ANDed together produce a logical low? 0 volts. What's X? The answer is the headache, because check it out. Those are low resistance wires. 5 volts to 0 volts with no resistance in between. Incredibly high current. It's not going to work for very long. Okay, you might assume that you're tying outputs together acts as an OR gate. It doesn't. It acts as a headache. You want to put an OR gate in there? Put an OR gate in there. Like I've said, I've seen that in textbooks, and I may have built something like that in the past that has given me a headache. Learn from my mistakes, learn from other mistakes. Don't tie outputs together. We will be doing some cross-coupling a little bit later where we're taking outputs, feeding it back to inputs, but that's a recommended practice. Don't do something like this. Okay, this kind of concludes the review of Unit 3. What have we gone over? We've gone over expanded inputs, i.e. gates with more than 2 inputs. We've gone over some additional gates, the NAND, its negative logic equivalent, the negative OR, the NOR, its negative logic equivalent, the negative AND, the exclusive OR, the exclusive NOR. We put those things in truth tables. We put those things in timing diagrams. We came up with the VHDL expressions. We did some multi-level logic. We came up with the VHDL expressions for that. We did some multi-level logic using a PLD, and we got a little precursor to the SOP expressions right here. And then we finally did the ultimate VHDL expression and did a little bit of lab review. Okay, this concludes the review of Unit 3, and we'll see you in lab, and we'll move on to Unit 4.